Jupiter is so large that it does not simply orbit the Sun in the way most of us imagine. It tugs back. The two bodies move around a shared centre of mass, and in Jupiter's case, that invisible point can lie above the Sun's own surface. That alone hints at something extraordinary. This is not just the biggest planet in the solar system, but a world whose gravity helps arrange the motion of everything around it. And yet, for all its scale and brightness, Jupiter keeps its most important secrets hidden beneath a cloud layer thinner than intuition would ever suggest. To understand why this planet matters so much, we have to begin with the giant we think we already know. Jupiter is the fifth planet from the Sun, sitting beyond the asteroid belt and between the orbits of Mars and Saturn. On average, it lies about 778 million kilometres from the Sun, or roughly 5.2 times farther out than Earth. 1 year on Jupiter lasts almost 12 Earth years, which means that since the dawn of modern astronomy, humanity has seen only a small number of true Jovian seasons pass. Even though seasons are subtle, Jupiter's axial tilt is only about 3 degrees, so unlike Earth or Mars, it does not lean enough to produce dramatic seasonal swings. In some ways that makes the planet feel steady and timeless. But that impression is deceptive. Even from a distance, Jupiter announces itself as something unusual. It is the largest planet in the solar system by far. Its diameter is about 11 times that of Earth, and its mass is 318 times greater. That would already make it enormous by any ordinary standard, yet Jupiter stands apart even more when you compare it to the rest of the planets together. Add up the mass of every other planet in the solar system, and Jupiter still outweighs them all by about 2.5 times. It contains almost all the non-solar planetary heft in our neighbourhood of space. That is why Jupiter is not merely another world circling the Sun. It is one of the main gravitational anchors of the solar system itself. We often picture planets tracing neat ellipses around a stationary Sun, as if the Sun sits fixed at the centre while everything else obeys. In reality, gravity is a mutual relationship. Every orbiting body pulls on the one it orbits. Usually the smaller object is so small that the effect is barely worth noticing. A space station pulling on Earth, or Mercury tugging on the Sun, changes almost nothing in any practical sense. But Jupiter is different. To see why, it helps to imagine two objects connected by an invisible bar. One is very heavy, the other much lighter. Their shared centre of mass will sit closer to the heavier object, but not exactly at its centre. Both objects move around that point together. In the case of the Sun and Jupiter, that point can actually sit outside the Sun's surface, about 1.68 solar radii from the Sun's centre. So as Jupiter travels around the Sun itself performs a subtle motion in response. They move around a common balance point in a slow gravitational dance. That image changes the way Jupiter feels. It is no longer just a distant, stripe-covered orb at the edge of the inner planet's world. It becomes a body so commanding that even the Sun cannot entirely ignore it. Jupiter is massive enough to leave fingerprints everywhere. Its gravity influences every major planet to some degree. It perturbs orbits. It captures moons. It shapes the paths of asteroids and comets. It may even have helped decide which worlds formed, which failed to form, and which survived long enough for something like Earth to emerge in the first place. And yet, for all that mass, Jupiter is not the densest planet. That distinction matters because it reveals something subtle about what Jupiter is. It is powerful not because it is unusually compact, but because it is immensely large. If Neptune were inflated to Jupiter's size, it would actually become the more massive world. If Jupiter were somehow compressed to Earth's size, Earth would be denser by far. Jupiter's dominance comes from volume, from vastness, from the staggering amount of matter gathered into one rotating planetary body. That difference between mass and density becomes important later, because it hints that Jupiter is not built like the rocky planets we know best. Still, mass has consequences, whether that mass is dense or diffuse. Jupiter's gravitational pull at its cloud tops is more than twice Earth's. If you could somehow stand there, which you cannot, the experience would be crushing. This gravity reaches far beyond the planet itself. Jupiter has collected dozens of moons and likely shaped the history of many smaller bodies that never became worlds in their own right. Some researchers think it disrupted ancient objects during the solar system's youth. Others have argued that its presence prevented more material from gathering into planets in certain regions. The solar system we inherited may be, in part, the solar system Jupiter allowed to exist. One of the most haunting examples of that long reach concerns Mercury. Mercury already follows a somewhat eccentric orbit close to the Sun, but Jupiter's gravitational influence contributes to the gradual perturbations that make long-term orbital predictions more unstable than intuition might suggest. On timescales of billions of years, those small nudges can matter. Models indicate that inner planetary orbits are not eternally fixed clockwork. They are stable enough for us, but not immune to chaos forever. Even there, far inward toward the Sun, Jupiter is part of the story. At the same time, Jupiter may be one of the reasons Earth has enjoyed such a long window of relative survival. The planet is often described as a kind of cosmic vacuum cleaner, though the phrase is only partly accurate. Jupiter does not simply swallow everything dangerous. Sometimes it captures objects, sometimes it redirects them. Sometimes it gives them an extra gravitational kick and sends them out of the solar system entirely. But the broader point remains. A world as massive as Jupiter changes the traffic pattern of space. Long-period comets and other hazardous bodies do not approach the inner solar system in quite the same way they would if Jupiter were absent. That makes Jupiter feel strangely double-sided. It is a destroyer and a guardian, a destabilizing force and a protective one. It tears apart, redirects, captures, and sometimes shields. It is the kind of planet that can ruin one orbit while preserving another. And this dual role helps explain why Jupiter matters so much beyond simple planetary trivia. To understand Jupiter is to understand something about the larger architecture of danger and survival in the solar system. For all its distance, Jupiter is not a hidden object. In fact, it is often one of the brightest sights in the entire night sky. After the Moon and Venus, Jupiter can become the third brightest natural object visible from Earth. At its most brilliant, it reaches a magnitude bright enough to stand out even to casual observers, and under dark skies it can cast faint shadows. That is remarkable when you remember how far away it is. A planet located 5 times farther from the Sun than Earth still shines so strongly in our sky that it becomes an easy target for even modest equipment. That visibility has helped make Jupiter one of the most observed objects in the solar system. Long before spacecraft ever arrived, astronomers studied it through telescopes and noticed something immediately compelling. Unlike a star, which remains a point of light, Jupiter resolves into a disk. Unlike a rocky planet, which often looks small and featureless, Jupiter shows patterns, belts, zones, colour, texture, change. Even amateur telescopes today can reveal the planet's broad striped appearance and, under good conditions, some of its more dramatic atmospheric features. It is one of the few planets that can look vividly alive even from a backyard. That sense of life is one reason Jupiter has always held such a strong grip on the imagination. It looks dynamic, it looks active, it looks like weather magnified to planetary scale. But appearance can be misleading. The cloud layer we actually see is surprisingly thin, only about 50 kilometers thick. On a planet this enormous, that is almost like a skin. Beneath that thin, visible surface lies the overwhelming majority of Jupiter's body, hidden from normal view. So the familiar striped face of Jupiter is real, but it is also just the outermost trace of a far deeper and stranger world. Even that visible layer raises difficult questions. Why does Jupiter look the way it does? Why the bands? Why the creams, browns, reds and oranges? Why does a giant planet so far from the Sun seem so visually dramatic? Part of the answer begins in the chemistry of the upper atmosphere. The clouds contain ammonia crystals, somewhat like those found on Saturn, but Jupiter's coloration is thought to involve compounds rising from deeper within the planet. These compounds, often referred to as chromophores, interact with ultraviolet light from the Sun and help create the multicolored bands that define Jupiter's appearance. What makes that process especially fascinating is that the pattern is stable in one sense and unstable in another. The latitudes of the major bands remain organized enough that astronomers can identify and track them over time, yet their width, tone, and visual character can change. Jupiter is not painted once and left untouched. Its face evolves. Material rises. Light alters chemistry. Atmospheric flows reorganize what we see. The planet keeps redrawing itself while still preserving a larger, underlying order. That balance between structure and turbulence is one of Jupiter's defining qualities. The broad banding suggests control, almost calm. But where those bands meet, instability thrives. Storms form, shear zones churn. Atmospheric motion becomes more violent and intricate. Jupiter's visible beauty comes from that tension between order and chaos. You are looking at a world where fluid layers race past one another at enormous scales, where chemistry and sunlight collaborate to produce colour, and where what seems serene at a glance is, on closer inspection, deeply restless. This is also where the story begins to tilt toward one of Jupiter's most famous mysteries. Because among those moving bands and turbulent boundaries sits a storm unlike anything on Earth, a feature so vast and so persistent that it has become almost synonymous with the planet itself. It is easy to treat it as a planetary landmark, a red oval that makes Jupiter instantly recognizable. But that storm is not just a decoration, it is a clue. A sign that the atmosphere of Jupiter is not merely active, but capable of sustaining structures on scales that stretch far beyond human weather, and for durations that challenge human intuition. Before we can understand that storm, though, we have to understand the kind of planet that could produce it. A world brighter than the stars around it, massive enough to tug the sun, thin-skinned, deep-bodied, chemically stained by material rising from below. A planet that seems familiar through a telescope, but grows stranger each time you look more carefully. And once the great red spot comes into view, Jupiter stops feeling like a distant giant and starts feeling like a problem we have only just begun to enter. What we see first when we look at Jupiter is not the planet itself in any full sense. It is the outer skin of a far larger and deeper world, a thin cloud deck stretched across a body so immense that the visible atmosphere becomes almost misleading. And yet that surface matters, because it is the only part of Jupiter that human eyes can meet directly. It is where colour, motion, chemistry and sunlight come together to produce the face that has fascinated observers for centuries. Those broad alternating bands, so clean at a distance and so turbulent up close, are the beginning of the puzzle. In visible light, Jupiter appears divided into belts and zones that wrap around the planet in parallel stripes. Some are pale and creamy, others darker and more reddish-brown, and together they create one of the most recognizable patterns in the solar system. But these are not painted layers sitting still on a solid surface. They are moving atmospheric regions, organized by powerful flows that circle the planet at different latitudes. The effect is elegant from afar. Through a telescope, Jupiter can seem almost orderly, as though nature has drawn carefully spaced lines across a polished sphere. The truth is far less calm. The cloud tops we see are made largely of ammonia ice. That alone makes Jupiter feel alien. These are not water clouds like the ones that drift over Earth. They form in a different chemical environment, under different pressures, in a world powered not only by sunlight from above, but also by heat rising from below. Even the brightness of the clouds tells a story. Some of the lighter regions appear to sit at higher altitudes, while darker and narrower regions can be shaped by lower cloud layers and the shadows cast by taller structures nearby. Jupiter's atmosphere has depth, layering, and relief. It is not a flat sheet of colour, but a textured, three-dimensional system. The colours themselves are still not completely understood, which is part of what makes Jupiter so compelling. The prevailing idea is that compounds rising from deeper within the planet reach the upper atmosphere and become exposed to ultraviolet light from the sun. That exposure alters them chemically. These colouring materials, often grouped under the name chromophores, are thought to be responsible for the reds, browns, oranges and yellows that spread across the cloud tops. In other words, Jupiter's appearance may be the visible consequence of an ongoing chemical cycle. Material rises, sunlight changes it, and then the atmosphere redistributes what has been altered. That means Jupiter's beauty is not static, its face changes over time. The major latitudes of its bands remain stable enough that astronomers can classify and follow them, but their widths can shift, their tones can deepen or fade, and local details can appear or vanish. One observation may make Jupiter look burnished and richly coloured. Another may reveal something paler, softer, or more fragmented. The planet keeps enough continuity to remain recognisable, but enough variability to remind us that this is weather on a scale far beyond weather as we know it. Jupiter is consistent in structure, but restless in expression. That restlessness becomes most obvious where the bands meet. These boundaries are regions of strong atmospheric shear, where neighbouring flows move at different speeds or in different directions. On Earth, interfaces like that can breed storms and instability. On Jupiter, the same basic principle is magnified to planetary scale. The most active turbulence often appears along these dividing zones, where the order of banded circulation gives way to eddies, whirls, and long-lived disturbances. The planet's iconic appearance is not separate from its violence. The stripes and the storms are part of the same system. This is what makes Jupiter's atmosphere so psychologically strange. On the one hand, it seems measured, almost disciplined, a giant wrapped in alternating lines that suggest order and repetition. On the other hand, every closer look reveals something unsettled. The more detail we resolve, the more that calm facade starts to break apart into knots, plumes, streaks, and vortices. Jupiter teaches the same lesson again and again. What looks simple from a distance is usually the visible trace of deeper complexity. No feature embodies that better than the Great Red Spot. It has become so famous that many people think of it almost as a permanent marking on the planet, like a giant eye staring back from the Jovian clouds. But the Great Red Spot is not a stain and not a crater. It is a storm, a vast rotating system embedded in Jupiter's atmosphere, and it has persisted for as long as we have been able to observe the planet in detail. Since it was first recorded in the 17th century, it has remained one of the most extraordinary examples of atmospheric longevity anywhere in the solar system. Its scale alone is enough to force a mental reset. The Great Red Spot has been large enough to fit the diameter of Earth within it. Even after shrinking from its earlier recorded size, it remains immense by any standard familiar to human weather. To call it a storm can feel almost inadequate, because the word carries habits of thought formed on Earth. We think of storms as brief things. They build, intensify, pass over, and disappear. On Jupiter, a storm can become part of the planet's long visual identity. It can endure across generations, across centuries, outlasting empires, telescopes, and scientific theories. And yet, even the Great Red Spot is not as fixed as it first appears. Over time, it has decreased in size. That fact is important because it reminds us that persistence is not permanence. The storm may be ancient by human standards, but it is still evolving. Its edges change. Its structure shifts. Its colour varies. At times it can appear rich brick red, and at others much paler, drifting toward tones so faint they are almost white by comparison. The Great Red Spot is iconic precisely because it lasts, but its lasting form is one of continual change. Its colour remains one of the most intriguing, unresolved questions. The leading idea again involves chemistry altered by sunlight. Compounds exposed to ultraviolet radiation may break apart or recombine in ways that produce the reddish hue. That mechanism would parallel what is thought to happen more broadly across Jupiter's upper atmosphere, but with one important difference. The Great Red Spot rises higher than the surrounding cloud deck, which means it may receive more direct interaction with sunlight than nearby regions. If so, the storm's stronger coloration would not be an accident of shape alone, but a visible consequence of altitude, exposure, and chemistry working together. That possibility makes the Great Red Spot even more revealing. It is not only a storm to admire, it is a probe into the structure of Jupiter's atmosphere. If its colour depends on how high it rises, and if its persistence depends on energy drawn from deeper layers, then the spot becomes a signpost pointing downward into the planet. It tells us that the visible cloud tops are linked to processes below, and that Jupiter's atmosphere cannot be understood as a shallow shell reacting only to sunlight from above. Something deeper is feeding motion, maintaining structure, and shaping the world we see. The storm is also physically elevated above neighbouring clouds, which changes the way it interacts with its surroundings. It is not simply spinning within a flat atmospheric plane. It stands higher, reaches into different conditions, and behaves differently because of that height. Over the centuries, observers have watched it distort, stretch, and shed filaments. Sometimes smaller features seem to interact with it, as though the atmosphere around it is in a constant negotiation with the giant vortex at its centre. It is stable enough to survive, but not isolated enough to remain untouched. And Jupiter does not stop at one scientifically remarkable storm. Another major feature, known as Red Spot Junior, formed when three smaller storms merged between the late 1990s and the year 2000. That alone is an extraordinary reminder of how Jovian weather works. Storms do not merely appear and vanish. They can collide, merge, reorganize, and become something new. Red Spot Junior survived its emergence and became a prominent feature in its own right, despite existing in the shadow of its far larger neighbour. In another setting that would already be astonishing, on Jupiter it feels almost like a secondary detail beside the older giant beside it. What features like these reveal is a planet that supports organised atmospheric structures across an astonishing range of scales. Jupiter can produce banded global circulation, towering cloud formations, localised turbulence, giant persistent vortices, and smaller storms that merge into new identities. It is a world of layered motion. Some patterns endure for centuries, others evolve over months or years, and all of them are embedded in a system driven by a balance of internal heat, rapid rotation, and atmospheric chemistry. The beauty of Jupiter is not ornamental. It is diagnostic. That is why visible light matters, even though it cannot show us everything. Human eyes alone cannot see beneath the ammonia cloud deck. They cannot reveal the deeper heat escaping from below, or the hidden structures that become obvious in infrared, ultraviolet, and microwave observations. But visible light gives us the first clues. It shows the topography of cloud heights through brightness and shadow. It reveals where chromophores gather and darken. It shows us where the atmosphere is smooth, where it is fractured, and where storms have grown so large that they become signatures of the whole planet. The visible face of Jupiter also carries a kind of emotional contradiction. It is beautiful enough to appear almost serene, but the more you understand it, the less serene it becomes. Those white pop-up clouds may be fresh material pulled upward from deeper levels. Those darker, redder stretches may have simply been exposed to sunlight longer, undergoing gradual chemical change. The belts and zones are not static ribbons, but moving streams. The spot is not a decorative blemish, but a storm whose depth and energy hint at far larger mechanisms beneath the surface. Jupiter invites wonder, then quietly replaces that wonder with unease. Because if this much motion, complexity and turbulence can exist in a cloud layer only tens of kilometers thick, what must be happening below it? What kind of world lies under an atmosphere that can organize itself into bands, sustain storms the size of Earth, and keep changing its visible expression decade after decade? The obvious answer is that Jupiter is not simply weather wrapped around emptiness. Its atmosphere is the topmost manifestation of an enormous planetary body, whose true nature still waits below the clouds, in layers where gas becomes something denser, stranger, and far less intuitive. That deeper world begins with a simple fact that is easy to say and surprisingly difficult to picture. Jupiter is made mostly of hydrogen and helium, the same two elements that dominate the Sun, but gathered here into a planetary body rather than a star. Roughly 90% of Jupiter is thought to be hydrogen, about 10% helium, with trace amounts of methane, ammonia, and other compounds mixed in. On paper, that sounds straightforward. In practice, it leads us into one of the strangest interiors in the solar system, because hydrogen does not behave the same way everywhere. Under enough pressure, it changes character. Near the upper atmosphere, hydrogen exists as a gas. Go deeper, and that gas becomes compressed into liquid form. Deeper still, under pressures so extreme that they are difficult to reproduce, and even difficult to imagine, hydrogen enters a metallic state. This is one of the most remarkable ideas in planetary science. The lightest and simplest element in the universe, the same element that drifts as a gas through space and ignites within stars, may inside Jupiter behave like a metal. That does not simply mean it becomes dense. It means its electrons move in ways that allow it to conduct electricity efficiently, helping create some of the most powerful large-scale effects associated with the planet. This layered descent from gas to liquid to metallic hydrogen is one reason Jupiter resists easy comparison with any world closer to home. On Earth, descending into the interior means moving from crust to mantle to core through familiar categories of rock and metal. On Jupiter, the boundaries are not so intuitive. There is no solid ground waiting beneath the clouds, no obvious surface where atmosphere ends and planet begins. Instead, the planet grades from one state to another, with pressure becoming the great sculptor of matter. Jupiter is not strange because it contains unusual ingredients. It is strange because ordinary ingredients are transformed there into unfamiliar forms. And then there is the question of what lies at the centre. Beneath the metallic hydrogen may sit a core made of rock, ice, or some combination of heavier material, but the details remain uncertain. Older models often imagined a relatively distinct central core. More recent thinking has become less confident about such a clean picture. The deepest regions of Jupiter may be less sharply separated than once assumed, with heavy elements mixed into surrounding layers, rather than confined in a simple, compact sphere. Even the word core can begin to lose its clarity here. What counts as a centre if the boundaries around it are blurred? That uncertainty is not a failure of effort. It is a consequence of the environment itself. We cannot fully recreate on Earth the immense pressures and temperatures found deep inside Jupiter, so our knowledge comes from indirect measurements, physical models, and the behaviour of matter under extreme conditions, pushed as far as experiments and theory can take us. That means Jupiter remains partly interpretive. We know enough to say it is dominated by hydrogen and helium. We know enough to infer enormous pressure and deep transitions in state. But when we ask exactly how those layers are arranged, or precisely what form the central region takes, the answers become softer. This is where Jupiter becomes especially humbling. For centuries, it seemed like a simple category of object, a gas giant. The phrase sounds almost complete, as if the label itself explains the world. But a label can hide as much as it reveals. Gas giant suggests something broad and comprehensible, a large ball of gas with storms on top. The closer science has looked, the less satisfying that shorthand has become. Jupiter is gaseous in its outer layers, yes, but deep inside it enters physical regimes that have more in common with high-pressure laboratories and theoretical materials science than with the ordinary meaning of gas. It is not merely a swollen atmosphere, it is a pressure-built world. Its bulk properties reflect that complexity. Jupiter is the most massive planet in the solar system, yet not the densest. That means it cannot simply be imagined as a rocky super-Earth scaled upward. Earth compressed to Jupiter's size would be something far heavier. Neptune inflated to Jupiter's dimensions would also outweigh it. Jupiter dominates because it gathered so much matter, not because each cubic piece of it is unusually dense. That distinction matters because it helps explain why the planet is so large and yet still so different from the smaller solid worlds. The giant planets belong to another category of planetary architecture altogether. Jupiter's rapid rotation adds another layer to the picture. It completes one full rotation in only about 10 hours, making it the fastest spinning planet in the solar system. That speed is astonishing when you remember the size of the object doing the spinning. A world more than 11 times Earth's diameter turns in less than half a day. But because Jupiter is not solid, it does not rotate as one rigid body. The poles take slightly longer than the equator. The difference is small in clock terms, only a matter of minutes, but scientifically it is profound. It means the planet's outer layers are moving according to fluid dynamics, not as fixed terrain locked to one central shell. That rapid spin changes the planet's shape. Jupiter is not a perfect sphere. Its equatorial radius is larger than its polar radius, giving it an obvious bulge around the middle. Rotation stretches it outward there, while gravity tries to pull everything inward. The result is a world flattened at the poles and widened at the equator. Even in silhouette, Jupiter carries the mark of its own speed. Its shape is physical evidence that this is a planet in motion, not just around the Sun, but within itself. For many people, especially when first learning about the planets, Jupiter raises an irresistible question. If it is made mostly of hydrogen, and if hydrogen powers stars, why is Jupiter not a star? At first glance, the logic feels intuitive. It is large, It is hydrogen-rich, and it seems like only a matter of quantity separates a giant planet from a dim red sun. But stars do not shine because hydrogen merely exists within them. They shine because pressure and temperature in their cores become high enough to trigger sustained nuclear fusion. That is the missing ingredient. Jupiter is immense, but not immense enough. Current understanding suggests Jupiter would need to be roughly 75 times more massive than it is now to become a true star. That is an extraordinary gap. It means Jupiter is not a near miss in any everyday sense. It sits far below the threshold for steady hydrogen fusion. The childhood idea that someone could somehow light Jupiter like a giant fuel tank also falls apart immediately. There is barely any oxygen there to support combustion in the first place, and even if there were, stars are not fires in the ordinary sense. They are fusion engines. Jupiter never became one. Still, the comparison is not entirely meaningless. Jupiter occupies an interesting borderland in our imagination because it shares some ingredients with stars while remaining firmly planetary. Its volume is not wildly removed from the smallest known red dwarfs, but mass matters more than mere size when it comes to ignition. In a way, Jupiter is a lesson in thresholds. Below a certain line, matter gathers into a giant planet. Above it, gravity squeezes hard enough for fusion to begin. Jupiter sits on the lower side of that divide, a reminder that in astronomy, a difference in mass can create a difference in destiny. And then, just when the interior begins to feel abstract and invisible, Jupiter offers an unexpected visible detail that most people do not associate with it at all. Jupiter has rings. Not grand, luminous, sprawling rings like Saturn, but a system of 4 planetary rings that quietly circle the planet nonetheless. The main ring is relatively thin and bright. The others are broader but exceptionally faint, so faint that they are easy to overlook beside Saturn's far more theatrical display. Yet their very existence matters, because they remind us again that Jupiter is not a simpler version of the giant planets. It is a fully complex system in its own right. The main ring is about 6,000 kilometers wide, and one of its most distinctive details is a notch-like feature, sometimes referred to as the Metis notch. Even the rings here seem understated, almost secretive. They do not define Jupiter in the popular imagination, but they belong to the same story of hidden complexity. A planet famous for bands and storms also possesses delicate structures of dust and debris orbiting around it. The closer we look, the more Jupiter refuses simplification. By now, a pattern is emerging. Every time Jupiter appears to settle into an easy category, it slips away again. It is a planet, but one made mostly of the same light elements as a star. It is not dense, yet it is massively dominant. It is gaseous above, liquid below, metallic deeper still. It may have a core, but perhaps not one that conforms to the neat boundary we instinctively expect. It spins so fast that its own shape reveals the strain. It wears rings. They're not the kind most people remember. Even before we turn to its magnetic environment or its moons, Jupiter already feels less like a single object, and more like an entire regime of physics gathered into one place. And that is why the visible cloud tops can no longer be taken at face value. The stripes and storms above are not the whole planet. They are symptoms of what lies beneath, expressions of a body shaped by pressure, speed, and internal structure at scales that push matter into states alien to our experience. Jupiter looks familiar enough to sketch from memory, but the moment we ask what it is under those clouds, ordinary planetary intuition starts to fail. The next clue comes from something we cannot see directly at all, an invisible force reaching far beyond the planet, born from that deep metallic interior and powerful enough to dominate everything moving around it. That invisible force is Jupiter's magnetic field, and once it enters the story, the planet stops being just a giant world and starts becoming an electrical system on a planetary scale. Magnetic fields are common enough in astronomy, but Jupiter's is extraordinary. It is immense, powerful, and deeply tied to the hidden structure of the planet below the clouds. The likely source lies in that layer of metallic hydrogen, where moving electrically conductive material, combined with Jupiter's rapid rotation, generates a field strong enough to reach far into surrounding space. What seemed in the last moments like an abstract interior detail now becomes something active and measurable, an unseen architecture extending outward from the planet. This magnetic field is by far the strongest of any planet in the solar system. If human eyes could see it, Jupiter would not appear as a neat, striped globe against darkness. It would be surrounded by a colossal, shifting magnetic environment stretching millions of kilometers into space. That region, known as the magnetosphere, is so large that if it were visible from Earth, it would appear larger than the full moon in our sky. In some directions, it extends outward on a scale that begins to feel less like a planetary feature and more like part of the solar system's weather itself. Jupiter does not merely sit inside space, it reshapes the space around it. That realization changes the way we think about observation. Visible light gave us Jupiter's banded face and its famous storms, but visible light alone cannot reveal the true reach of the planet. To understand Jupiter, astronomers had to stop relying only on what the eye naturally sees and begin reading the planet across the electromagnetic spectrum. In astronomy, light means much more than the narrow slice of colour our eyes can detect. It includes infrared, ultraviolet, radio waves, and other forms of radiation, each carrying different information about temperature, chemistry, motion, and energy. Jupiter turned out to be a perfect example of why that broader way of seeing matters. In visible light, the planet looks familiar enough, but shift into infrared and a new Jupiter appears. Infrared observations can trace heat escaping from deeper layers and show where thinner cloud regions allow warmth from below to leak upward more effectively. Bright infrared regions do not always correspond to the brightest clouds in visible light. Sometimes a place that looks visually calm reveals itself as a window into deeper and hotter atmospheric levels. This is one of the great gifts of invisible light. It breaks the illusion that the visible surface tells the whole story. On Jupiter, the visible cloud tops are often more like a curtain than a wall. This matters especially when studying storms. A storm that appears as a coloured swirl in ordinary images can, in infrared, reveal differences in height, temperature, and structure that the eye would otherwise miss. High cold clouds may stand out differently from lower warmer ones. Deep atmospheric disturbances can become easier to track. Regions that seem uniform in colour can split into distinct thermal patterns once seen through the right wavelengths. Jupiter's atmosphere is not just a picture, it is a layered thermal engine, and infrared light lets us begin reading its hidden contours. Ultraviolet light adds yet another perspective. Instead of simply tracing heat, it can help reveal how high-altitude particles and gases interact with sunlight and magnetic processes. It also contributes to our understanding of the planet's auroras, which are among the most powerful in the solar system. On Earth, auroras are already one of nature's most beautiful atmospheric events, driven by charged particles guided into the upper atmosphere by the magnetic field. On Jupiter, the same basic principle operates on a far larger and more violent stage. The result is not just a pretty light show, but a sign of an enormous, energetic system connecting the planet, its magnetic field, and its moons. These auroras are especially intense because Jupiter's magnetosphere is not fed only by the solar wind. It is also powered internally by the planet's own rotation and by material supplied by its moons, especially Io. That means Jupiter's auroral regions are not just passive responses to the Sun. They are part of a self-sustaining planetary machine. Invisible light reveals this in a way visible light never could. Once again, Jupiter proves that what seems most dramatic in ordinary images is often only a fragment of the deeper truth. Another essential tool is spectroscopy, the technique of splitting light into its component wavelengths to identify the fingerprints of different materials. Every element and molecule interacts with light in distinctive ways. By studying those patterns, scientists can infer what Jupiter's atmosphere contains and how those materials are distributed. This is how the chemistry of ammonia, methane, and other atmospheric components becomes legible from a distance. Jupiter cannot be sampled by standing on its surface because there is no ordinary surface to stand on, so light becomes the sample. The planet writes its own atmospheric report into the radiation it reflects, emits, and absorbs. That has allowed astronomers to go far beyond surface impressions. The cloud bands are not merely coloured stripes, but chemically and dynamically distinct regions. Variations in brightness can reflect different cloud heights. Differences in color may indicate different exposure to sunlight or different concentrations of atmospheric compounds. Spectral observations help separate these factors and show that Jupiter's appearance is not decorative but diagnostic. The atmosphere tells on itself through light, provided we learn how to listen. False color imaging has also become one of the most powerful ways of communicating Jupiter's hidden structure. These images do not show the planet as human eyes would see it. Instead, they assign visible colors to data gathered from non-visible wavelengths, so that differences in temperature, altitude, composition, or energy become easier to interpret. At first, this may seem artificial, but in a deeper sense, it is more truthful than ordinary vision. Human sight evolved for life on Earth, under Earth's sun, within Earth's atmosphere. Jupiter demands a different kind of perception. False color is not deception, it is translation. Few places demonstrate that better than Jupiter's poles. For a long time, the poles remained comparatively mysterious because most earlier spacecraft saw the planet from angles that emphasized its equatorial regions. Popular images of Jupiter taught us to think of it as a banded world wrapped in horizontal stripes. But when later missions began observing the poles more directly, the image shattered. The polar regions are not dominated by the same broad belts and zones that define lower latitudes. Instead, they're crowded with cyclones, immense storm systems packed together in geometries that feel almost unreal. This was one of the most visually startling revelations in modern Jupiter science. The planet we thought we knew had hidden an entirely different atmospheric personality at its ends. The North Pole and South Pole both host clusters of giant cyclones, arranged around central storms in ways that seem almost organized and yet remain dynamically active. It is as though Jupiter contains multiple atmospheric styles at once. Around the middle, it appears banded and streamlined. Near the poles, it becomes chaotic, crowded, and strangely symmetrical. The same planet sustains both. Visible light hinted at none of this clearly enough. It took new ways of seeing to bring the poles into focus. And once they came into view, they forced a revision of the mental image many people had carried for years. This is an important pattern in Jupiter science. Every major leap in understanding has come from widening the range of what counts as observation. The eye alone gave us recognition. Instruments gave us understanding. Each wavelength added another layer, and each layer complicated the planet rather than simplifying it. There is something philosophically striking about that. Jupiter is bright, obvious, impossible to miss in the sky, and yet the more scientifically important aspects of it are often the ones invisible to unaided human senses. The heat patterns, the chemical signatures, the auroras, the scale of the magnetosphere, the hidden organization of the poles, none of these could be appreciated fully through ordinary vision. Jupiter was never just waiting to be looked at, it had to be decoded. In a sense, the planet demanded that we expand our idea of sight before it would reveal its real character. And that expansion did more than refine old knowledge, it overturned assumptions. A person relying on traditional images might think of Jupiter as a striped globe with one famous red storm. A scientist reading the full spectrum sees a planet with deep heat leakage, complex chemistry, astonishing auroras, colossal magnetic influence, and polar cyclone systems unlike anything early observers expected. The difference between those two pictures is not minor. It is the difference between seeing Jupiter as an object and seeing it as a system. That is why this stage of the story matters so much. Until now, Jupiter has already shown itself to be massive, dynamic, chemically rich, and physically strange. But those traits were still filtered through distance and partial vision. The next leap comes when a spacecraft is sent not just to glance at Jupiter, but to live with it closely enough and from unusual enough angles to test old models against direct measurements. Once that happens, familiar ideas start to crack. The giant planet we thought we had gradually learned to read begins revealing structures, anomalies, and surprises that push even expert expectations off balance. That spacecraft is Juno, and with its arrival, the story of Jupiter changed from careful inference to something closer to direct confrontation. Juno did not approach the planet the way many earlier missions had. Instead of circling mainly above the equator, it was placed into a long polar orbit that carried it over the top and bottom of the world, sweeping past the cloud tops and then far back out again. That choice was more than a technical detail, it was a new way of asking questions. To see Jupiter properly, scientists had to stop looking at it from the familiar side and begin crossing over the regions that had remained hidden for so long. Even that orbit came with danger. Jupiter is surrounded by intense radiation belts, charged particle environments so extreme that they can damage electronics and shorten missions dramatically. Juno had to move through one of the harshest radiation settings any spacecraft has ever endured around a planet. Parts of its path were chosen specifically to reduce exposure, and its most sensitive systems were heavily shielded. The mission was not just a scientific gamble, it was a survival challenge. Every close pass represented an encounter with a world whose invisible environment could be as threatening as its visible size was majestic. But the reward was immediate. Juno's views of Jupiter's poles revealed a planet that did not match the textbook image fixed in popular memory. Instead of neat bands continuing all the way upward and downward, the poles showed sprawling cyclone fields, immense storms locked into patterns around central vortices. They looked less like the organized Jupiter of classic telescope images, and more like something almost biological, cellular clusters of motion packed together around a rotating axis. The familiar planet had not been replaced. It had been expanded. Jupiter turned out to contain atmospheric regimes so different from one another that the old one-image summary no longer held. That alone would have justified the mission. But Juno went much further than imaging. It carried instruments designed to probe beneath the cloud tops and into the atmospheric and interior structure of the planet. The goal was not only to photograph Jupiter, but to weigh its hidden layers, to sense its magnetic behavior, to study its gravity field, and to examine how material is distributed through the atmosphere. The result was a new Jupiter, not in the sense that the planet changed, but in the sense that our confidence in older simplifications began to dissolve. One of the most important findings involved ammonia. Before Juno, scientists already knew ammonia played a major role in the visible cloud chemistry of Jupiter. But the new observations showed that ammonia was not distributed in the simple, smoothly mixed way many had imagined. Instead, it formed complex patterns that extended deep into the atmosphere, with concentrations varying by latitude and depth. That mattered because ammonia is not just another trace ingredient. It is a marker of atmospheric circulation, a clue about how material rises, sinks, and moves through Jupiter's deeper weather system. The visible bands at the top were no longer just surface decoration. They were linked to structures reaching far below. This was one of Juno's most profound contributions. It showed that Jupiter's atmosphere could not be treated as a shallow weather layer detached from the deeper planet. The banded circulation extended downward much farther than some had expected, perhaps thousands of kilometers. That changes the meaning of every visible feature. A stripe on Jupiter is not simply a pattern painted across the upper clouds. It may be the top expression of a deep, moving column within the planet's atmosphere, part of a circulation system rooted far below the level where sunlight first touches the cloud tops. Then there was the interior. For a long time, the question of Jupiter's core had hovered over planetary science like a partly solved riddle. Was there a compact central core of heavy elements? If so, how large was it? How sharply was it separated from the surrounding hydrogen and helium? Juno's gravity measurements complicated that picture. Rather than confirming a neat, dense core surrounded by cleaner layers, the data pointed towards something blurrier, a more diluted or fuzzy central region where heavy material may be spread over a larger volume than older models had predicted. In other words, Jupiter may not have the crisp internal architecture many people instinctively imagine. That possibility matters because it reaches all the way back to how giant planets form. A sharply defined core fits one style of planetary growth more comfortably. A diluted central region suggests a more turbulent and dynamic history, perhaps involving mixing, impacts, or long-term redistribution of material under extreme conditions. Juno did not hand scientists a final answer in simple terms. Instead, it replaced a tidy picture with a richer and less settled one. The core question was not closed, it was opened wider. The magnetic field told a similar story. Jupiter's magnetism was already known to be immense, but Juno's close measurements showed that it was also unexpectedly irregular. Some regions were far stronger or more oddly structured than anticipated, including a striking area of intense magnetic complexity that stood out as a kind of anomaly. This suggested that the dynamo generating the magnetic field within Jupiter might not be operating in the smooth, globally symmetrical way older models often preferred. The deep conductive region was doing something more intricate. Once again, the mission took an apparently understood fact and made it more puzzling. Juno also revealed auroras of astonishing power and complexity. Jupiter's auroras had already been known as major features of the planet's upper atmosphere, but the mission showed them in new detail and linked them more clearly to the giant magnetic and particle systems surrounding the planet. On Earth, auroras are often interpreted as elegant atmospheric reactions to charged particles from the Sun. At Jupiter, they become something broader and more intense, shaped not only by solar input, but by the planet's own magnetic engine and by the material pouring into that system from its moons. Juno made those auroras feel less like atmospheric decoration and more like the luminous edge of an electrical empire. And yet perhaps the most quietly unsettling discoveries came from storms and lightning. We know lightning on Earth as a phenomenon tied to water clouds, convection, and the separation of charge in storm systems. Jupiter also produces lightning, but the details do not mirror Earth neatly. Juno detected powerful lightning and storm activity at altitudes where the traditional expectations for liquid water behavior were less straightforward. The atmosphere was doing something more complicated than a direct Earth-scale analogy would suggest. Once again, Jupiter reminded us that familiar language can conceal unfamiliar physics. This is where one of the strangest ideas from the mission enters the story: mushballs. The term sounds almost playful, but the process it describes is a serious and surprising atmospheric mechanism. In Jupiter's violent upper storms, ammonia and water may combine into slushy hail, like bodies that form high in the atmosphere and then fall deeper downward, carrying ammonia with them. These mushballs can help explain why ammonia appears depleted in some upper regions and redistributed at greater depths. It is an elegant solution to a puzzling observational pattern. More than that, it is the sort of idea only Jupiter could produce, a weather process that sounds alien because it is alien. Think about what that means. On Earth, weather rearranges water. On Jupiter, deep storms may be manufacturing falling lumps of ammonia water slush that transport chemistry vertically through a vast atmosphere. The giant planet is not just windy or stormy in a generalized sense. It operates with materials, scales, and mechanisms that force us to enlarge the very category of weather. Juno did not merely confirm Jupiter's turbulence, it made that turbulence more specific, more physical, and far stranger than many people had realized. This growing specificity has had an interesting emotional effect on Jupiter science. Earlier generations often spoke of the planet in grand, broad terms. The largest planet, a gas giant, home of the Great Red Spot, ruler of many moons. Those descriptions were true, but they left a comfortable amount of vagueness in place. Juno removed some of that vagueness and replaced it with a more intimate uncertainty. The closer we moved to Jupiter, the less it behaved like a solved archetype, and the more it resembled an active laboratory full of unresolved processes. That can feel paradoxical. Better data should make a world seem clearer. In Jupiter's case, better data also made it stranger. This is often how science really progresses. A mission does not arrive and erase mystery. It sharpens it. It strips away the wrong confidence and reveals the real questions hiding underneath. Juno did that repeatedly. The poles were not what people imagined. The ammonia structure was deeper and more uneven than expected. The core was less sharply defined. The magnetic field was more irregular. The auroras were more intense and internally driven. The storms were producing phenomena as strange as mushballs. Piece by piece, the mission reintroduced Jupiter to us. And the most important consequence may be the simplest one. Juno proved that Jupiter is not only a giant version of planetary processes we already know. It is a world with its own logic, one that overlaps with Earth in certain basic physical principles, but diverges in execution almost everywhere that matters. Gravity, chemistry, Fluid motion, electricity and heat all operate there according to familiar laws, but under such different conditions that the outcomes become deeply unfamiliar. This is what makes Jupiter scientifically valuable. It is not a remote echo of home. It is a new environment for testing what planetary systems can be. Once that becomes clear, the next step feels inevitable. Jupiter can no longer be understood as a single isolated globe, however rich its atmosphere and interior may be. Its full significance emerges only when we turn outward and see what exists within its gravitational reach. Because surrounding this giant are worlds that should, by any reasonable expectation, be minor companions. Instead, they form a system of their own, with fire, ice, radiation, deep oceans, and perhaps even conditions where life could persist far from the warmth of the sun. Those worlds begin with one of the most important moments in the history of astronomy. In the year 1610, Galileo Galilei turned a telescope toward Jupiter and saw 4 small points of light near the planet. More importantly, he watched them change position night after night. They were not fixed stars, they were bodies orbiting Jupiter itself. That observation shattered something deep in the old picture of the cosmos. Not everything revolved around Earth. There were smaller systems nested within the larger one. Even now, centuries later, the power of that discovery has not faded. Jupiter was not just a planet. It was evidence that nature builds hierarchies. Those 4 moons, Io, Europa, Ganymede, and Callisto, are still known collectively as the Galilean moons, and together they transform Jupiter from a single giant planet into the centre of a miniature planetary system. They are not minor variations on one theme. They are dramatically different worlds, shaped by the same parent planet, but pushed into radically different destinies. One is the most volcanically active body in the solar system. Another may conceal a global ocean beneath ice. Another is the largest moon in the solar system and carries its own magnetic field. The outermost of the 4 is an ancient, cratered archive of deep time. The closer we study them, the less they feel like moons in the ordinary sense. They feel like worlds. That difference begins with Jupiter's gravity. To orbit a planet this massive is to live inside a relentless field of tidal stress, magnetic influence, and radiation. Distance from Jupiter matters enormously. So does orbital resonance, the repeated gravitational timing that locks some moons into patterns that flex and heat them internally. Jupiter is not only the body these moons orbit, it is one of the main reasons they are what they are. The giant planet pulls on them, distorts them, bathes them in radiation, and in some cases, indirectly powers their geology. You cannot tell the story of the moons without telling the story of Jupiter acting through them. Io, the innermost of the Galilean moons, is where that relationship becomes most violent. At first glance, its position might suggest little more than proximity, but proximity to Jupiter is destiny. Io is caught in a gravitational rhythm with Europa and Ganymede that keeps its orbit slightly elliptical instead of allowing it to settle into a perfect circle. That slight eccentricity means the tidal pull on Io changes continuously as it moves around Jupiter. The moon is squeezed and released, over and over again. That repeated flexing generates heat inside the moon, and on Io, the heat is so extreme that it powers a world of constant volcanism. The result is unlike anything else in the solar system. Io is not merely geologically active, it is eruptive on a planetary scale. Its surface is dotted with volcanoes, lava flows, and sulfur-rich deposits that paint the moon in yellows, reds, whites, and dark patches. Plumes can rise high above the surface. Entire regions can be resurfaced by fresh volcanic material. While Earth's geology is shaped by plate tectonics, erosion, oceans, and an atmosphere, Io seems to live in a more direct state of internal release. It is a world where gravity from a parent planet is translated into fire. That alone would make Io extraordinary, but Jupiter's magnetic field adds another dimension. As Io moves through the giant magnetosphere, it interacts electrically with the surrounding plasma environment. The moon contributes material to that environment, especially through volcanic gases that become ionized and trapped. In this way, Io is not only a moon being acted upon by Jupiter, It actively feeds the Jovian system around it. Material from Io helps populate the torus of charged particles surrounding Jupiter, and that in turn plays into the planet's auroras and magnetic behavior. Io is a volcanic world, but it is also a participant in an electrical relationship with the planet it circles. Move outward to Europa, and the tone shifts almost violently from fire to ice. Europa's surface is one of the smoothest in the solar system, bright and cracked, marked by long dark lines and broken regions that suggest motion and stress within the ice shell. Compared with Io, Europa looks quiet, but that quiet is deceptive. Beneath the surface, strong evidence points toward a global liquid water ocean hidden below the ice. If that ocean exists in the way many scientists now suspect, Europa may contain more liquid water than all of Earth's oceans combined. Suddenly, the Moon stops being a frozen ornament and becomes one of the most compelling places in the solar system. Europa's ocean is thought to persist for a reason that echoes Io, though in a less extreme form. Tidal interactions with Jupiter flex the Moon's interior, generating heat that may help keep water from freezing solid all the way through. The surface cracks may be signs of that restless internal life. Some areas appear as chaos terrain, where broken blocks of ice look as though they were disrupted and shifted, perhaps by movement or partial melting below. There have also been tantalizing hints of plumes, possible jets of material rising above the surface, though this remains an area of active investigation. Every clue points in the same general direction. Europa is not dead. It is active, hidden, and potentially habitable. That last word changes everything. Habitability does not mean life is present. It means conditions may exist that could support life as we understand it. Europa is especially compelling because it may bring together three ingredients that planetary scientists care about deeply: liquid water, the chemistry of mineral-rich rock below, and a source of energy. On Earth, where water, chemistry, and energy meet, life takes hold with astonishing persistence. If Europa's ocean contacts a rocky seafloor, and if chemical gradients exist there, then an environment far from sunlight could still host processes that resemble the deep ocean ecosystems of Earth. The possibility is not proof, but it is enough to make Europa one of the most scientifically charged destinations in planetary exploration. Then there is Ganymede, which is easy to overlook only because its quietness is less dramatic than Io's fury or Europa's mystery. But Ganymede is extraordinary in a different way. It is the largest moon in the solar system, larger even than the planet Mercury, though less massive because of its composition. Size alone would be enough to make it notable, yet Ganymede adds another rare distinction. It is the only moon known to possess its own intrinsic magnetic field. That means it is not just responding passively to Jupiter's magnetism. It has an internal dynamo of its own, a profound hint that its deep interior is active and differentiated in ways that matter. Its surface records a long and complex history, with darker, older regions and lighter, grooved terrain, suggesting tectonic or cryotectonic processes in the past. Like Europa, Ganymede is also thought to harbour subsurface oceans, though likely arranged in more complex layered structures. This makes it scientifically rich in its own right. It is a world large enough to sustain internal organisation, magnetically distinct enough to stand apart from other moons, and geologically varied enough to preserve multiple eras of its history in visible form. Ganymede does not demand attention through spectacle in the same way Io does. Instead, it rewards deeper attention by revealing just how many planetary traits a moon can develop under the right conditions. And then there is Callisto, the outermost of the four, and in some ways the most quietly haunting. Where Io is renewed by volcanism, and Europa may be reshaped from below, Callisto seems ancient. Its surface is battered by impact craters, so heavily marked that it appears to preserve a record stretching back through much of solar system history. To look at Callisto is to see time accumulated rather than erased. It lacks the same obvious signs of intense tidal heating that define the inner Galilean moons, because it lies farther from Jupiter and is less strongly flexed by gravitational resonance. But that apparent passivity makes it valuable in a different way. Callisto is a memory surface. That ancient character does not necessarily mean simplicity. There are reasons to suspect that even Callisto may hide an ocean beneath its crust. If so, then all three of the outer Galilean moons could, in different ways, be ocean worlds, despite their strikingly different surfaces. This is one of the most powerful lessons Jupiter's system teaches. Similar starting materials placed at different distances from a giant planet can diverge into dramatically different outcomes. One world becomes a volcanic furnace, another becomes an ice shell over a hidden sea, another grows into a magnetized giant moon, another preserves the scars of deep time or perhaps still holding liquid water below. The diversity is not random. It is structured by Jupiter's influence. Seen together, the Galilean moons feel less like satellites and more like a natural experiment in planetary possibility. They show what gravity, resonance, radiation, and internal composition can do when allowed to interact over billions of years. They also expand the meaning of what a planetary system can be. Around the Sun we have planets. Around Jupiter we find, in miniature, many of the same themes: geological activity, magnetic fields, internal oceans, surface evolution, atmospheric interaction, even the possibility of habitable environments. Galileo's insight was not just that moons orbit Jupiter. It was that nature repeats its patterns across scales. This is why Jupiter cannot be understood in isolation. Its moons are not accessories to the main attraction. They are part of the reason Jupiter matters so much scientifically. The giant planet becomes more than a destination because it presides over a system where some of the most extreme and compelling environments in the solar system exist side by side. Fire and ice, radiation and ocean, ancient surface and hidden interior, violent interaction and quiet preservation. All of it held together within one gravitational domain. And among those worlds, one question begins to rise above the others. Not which moon is most beautiful, or even which is most extreme, but which might come closest to answering one of the deepest scientific questions we know how to ask. Because once you accept that liquid oceans may exist in darkness beneath ice, warmed not by sunlight but by tidal energy and internal chemistry, the search is no longer only about strange moons around a giant planet. It becomes a search for whether life might take hold in places the old imagination would never have considered. That possibility changes the emotional center of Jupiter's system. Until now, the moons may have seemed like marvels of geology and physics, each extraordinary in its own way. But once the question of life enters the frame, the stakes become different. We are no longer asking only how these worlds work. We are asking whether one of them might host chemistry that has crossed the threshold into biology. And that question becomes most powerful on Europa, where a frozen exterior may be hiding an ocean world in complete darkness, sealed away from space and sunlight for perhaps billions of years. Europa's appeal lies in the convergence of several facts that, taken together, are difficult to ignore. There is strong evidence for a global ocean beneath the ice. There is continual tidal stressing from Jupiter's gravity, which provides a plausible long-term energy source. And there is reason to think the ocean may interact, directly or indirectly, with rocky material below. If that is true, then Europa may possess the three broad ingredients that make planetary scientists pay close attention: liquid water, energy, and chemistry. None of these alone guarantees life, but all of them together create one of the best natural laboratories in the solar system for asking whether life requires sunlight at all. On Earth, the link between life and sunlight feels obvious because the surface biosphere is saturated with it. Plants, climate, and ecosystems are tied to solar energy so deeply that it becomes easy to forget that sunlight is not the only energy source biology can use. In Earth's deep oceans, far below where light can penetrate, hydrothermal vent ecosystems thrive on chemical gradients rather than daylight. There, hot, mineral-rich fluids rise from the seafloor and create environments where microorganisms draw energy from chemistry itself. If something comparable exists on Europa's ocean floor, not identical but functionally similar, then the Moon could host habitable niches utterly unlike any landscape we usually imagine when we think about life. This is what makes Europa feel so intellectually destabilizing. It asks us to detach life from the image of blue skies, shallow seas, and green continents. It asks whether biology could begin or persist under a roof of ice tens of kilometers thick, in an ocean no human eye has ever seen, on a moon orbiting a giant planet in the cold outer solar system. That sounds almost mythic at first, but the physics behind it are serious. Water can remain liquid if heated from below. Tides can provide that heat. Rock-water interactions can provide chemistry. And once those pieces are in place, the old assumption that habitable worlds must sit in warm sunlight begins to feel much smaller than it once did. Europa's surface gives us the first clues to that hidden interior. The moon is crisscrossed by long, dark fractures and ridges that suggest repeated stressing, cracking, and reworking of the icy shell. Some regions look as though the surface has been broken into rafts and shifted, then partially refrozen in new patterns. These chaotic terrains have attracted enormous attention because they hint at exchange between the surface and what lies below. If warm ice or liquid water has risen upward, or if the shell has thinned enough in places to allow deeper material to influence the surface, then those broken landscapes may be windows into processes happening far beneath the visible crust. There have also been tantalizing signs that Europa may occasionally vent material into space. Possible plume detections have remained difficult and debated, but even the possibility matters. A plume would be scientifically precious because it could carry material from the subsurface ocean upward, where spacecraft might sample it without needing to drill through kilometers of ice. That would not solve the mystery in one stroke, but it would transform the search from inference to direct investigation. Instead of only reading the moon from its surface fractures and geophysical signatures, we could begin tasting something of its hidden ocean through the particles it releases. And yet, Europa is not a gentle place. Jupiter's radiation belts are ferocious, and Europa orbits deep within that hostile environment. The surface is constantly bombarded by energetic particles. That means any life near the topmost ice would face severe conditions, and it also means the surface chemistry itself is being altered continuously by radiation. Oddly, that may not be entirely bad from a habitability standpoint. Radiation at the surface can create reactive compounds that, if transported downward into the ocean, might provide useful chemical energy. Once again, Jupiter's danger and scientific promise become intertwined. The very environment that makes Europa so harsh to visit may also contribute to the moon's astrobiological interest. Ganymede adds another layer to this story. It may not command the same singular attention as Europa in the search for life, but it broadens our understanding of how ocean worlds can exist. Ganymede likely contains vast amounts of water beneath its surface, perhaps organized in multiple layers, separated by high-pressure forms of ice. That complexity makes the habitability picture less straightforward than on Europa, where the possibility of ocean contact with rock is especially important. Even so, Ganymede matters because it demonstrates that large moons can sustain differentiated interiors, magnetic activity, and long-lived subsurface water reservoirs. It widens the category. Europa may be the most urgent target, but Ganymede shows that hidden oceans in the outer solar system may not be rare exceptions. Its intrinsic magnetic field makes Ganymede especially fascinating. A moon generating its own dynamo is not just a curiosity. It means the body has internal structure and motion sufficient to create global magnetic behavior, something that speaks to a rich thermal and compositional history. That field also creates a small magnetosphere nested within Jupiter's much larger one, an almost unbelievable arrangement when you pause to picture it. A moon with its own magnetic shield living inside the magnetic empire of a giant planet. Scientifically, Ganymede stands at the intersection of planetary interiors, magnetic dynamics, and ocean world research. Even if it turns out to be less directly habitable than Europa, it remains essential to understanding how such worlds evolve. Then there is Callisto, often quieter in the public imagination, but increasingly important when discussions turn from pure astrobiology to long-term exploration. Callisto lies farther from Jupiter, beyond the worst of the radiation belts that plague Europa and Io. That relative safety makes it attractive as a potential staging point for future human operations in the Jovian system. A base on or around Callisto would still face extraordinary technical challenges, but compared with the intense radiation closer in, it occupies a far more workable environment. In that sense, Callisto may become important not because it is the most likely place to find life, but because it may be the best foothold from which humans could study the other moons more directly. Callisto may also harbour a subsurface ocean of its own, though the evidence and implications are different from Europa's case. If liquid water does exist below its battered crust, then Callisto joins the growing family of hidden ocean worlds that force us to rethink what counts as a potentially active environment. But even apart from that possibility, its ancient cratered surface gives it value as a record keeper. While Io is constantly resurfaced, and Europa may be repeatedly renewed by internal activity, Callisto preserves scars. It is a library of impacts, a long memory written into ice and rock. That alone makes it crucial for reconstructing the history of the outer solar system. Taken together, these moons change the meaning of Jupiter itself. The giant planet is no longer simply an object of interest because of its mass, storms, or magnetic field. It becomes the central body of a system where some of the most profound scientific questions in modern planetary research converge. How do tidal forces sustain geological activity over billions of years? How common are hidden oceans beyond the traditional habitable zone? Can life emerge in darkness, driven by chemistry instead of sunlight? How do magnetic environments shape the evolution of moons? What kinds of worlds can giant planets create and maintain around them? Jupiter does not answer these questions alone. It gathers them into one place. That is why the future of exploration around Jupiter feels so charged. Missions aimed at Europa and the broader Jovian system are not just follow-ups to old discoveries. They are attempts to push beyond the era of suspicion and into the era of testing. We already suspect that oceans exist. We already suspect that tidal heating matters. We already suspect that chemistry and energy may coincide in meaningful ways beneath the ice. The next step is to examine, measure, and search for signatures strong enough to move those suspicions toward firmer conclusions. In that sense, the story of Jupiter's moons is still in its opening stages, and behind all of it stands the larger planet itself, whose gravity created this diversity, whose radiation shapes it, and whose presence may have influenced not only the evolution of its moons, but the history of the entire solar system. Once the possibility of hidden life and future exploration enters the frame, Jupiter stops being merely the largest planet. It becomes part of a much larger question about why our solar system looks the way it does, how dangerous it has always been, and whether the giant world out beyond the asteroid belt has done more than dominate its neighbourhood. It may also have helped make our own world survivable by intercepting catastrophes that might otherwise have reached Earth. That protective role is one of the most dramatic and most debated parts of Jupiter's story, and to understand why it matters, we have to watch the planet do something few worlds ever do in plain view. In July of 1994, fragments of comet Shoemaker-Levy 9 slammed into Jupiter after the comet had first been torn apart by the planet's gravity. The impact was not a subtle event. It was the largest planetary explosion ever witnessed directly by human observers. Dark scars spread across Jupiter's atmosphere, each one marking a collision of such scale that for a moment the solar system stopped feeling ancient and orderly and began to feel immediate, violent, and unfinished. The story began before the actual impacts, when the comet passed too close to Jupiter and crossed inside the Roche limit, the distance at which tidal forces can overwhelm the self-gravity of a weaker body. Jupiter did not merely attract the comet, it pulled it apart. Shoemaker-Levy 9 broke into a chain of fragments, creating one of the strangest and most memorable sights in modern astronomy. A shattered object stretched into a string of pieces, all following nearly the same doomed path. By the time those fragments finally struck Jupiter, the event had already revealed something profound. A giant planet's gravity does not simply steer other bodies, it can destroy them before they ever arrive. When the impacts came, they left visible marks that were large enough to be seen from Earth. That fact alone was astonishing. We were not watching a minor atmospheric disturbance, we were seeing the after effects of collisions powerful enough to bruise the face of the largest planet in the solar system. The scars persisted long enough to be tracked as Jupiter rotated, and they became a public reminder that catastrophic impacts are not relics of some distant, chaotic past. They still happen. The solar system is calmer than it once was, but it is not calm in any final sense. Scientifically, The Shoemaker-Levy 9 event was a gift hidden inside a catastrophe. As the fragments plunged into Jupiter's atmosphere, they excavated and heated material, exposing chemistry and structure that would otherwise have remained more difficult to study. The impacts became a natural probe, an accidental experiment no mission planner could have designed. Astronomers were able to watch how Jupiter's atmosphere responded, how debris spread, how deep material was brought upward, and how such a giant planet absorbs violence. It was one of those rare moments when destruction became revelation. But the deeper significance of the event lies in what it says about Jupiter's place in the solar system. A world this massive intercepts objects. It perturbs them, captures them, shreds them, and sometimes takes the hit itself. That does not make Jupiter a perfect shield. The idea of Jupiter as a simple cosmic bodyguard is too neat. In some orbital circumstances, a giant planet can also redirect dangerous objects inward, increasing risk for the inner system rather than reducing it. Gravity is not moral. It does not protect by intention. It acts according to trajectories, mass, and timing. Even so, the broader pattern remains hard to ignore. Jupiter changes the impact environment of the solar system in a major way. Many long-period comets, in particular, are thought to be intercepted or deflected by Jupiter far more often than they are allowed to reach the inner planets. Estimates suggest that the giant planet is struck by such bodies orders of magnitude more frequently than Earth. That makes intuitive sense. Jupiter presents a much larger target, and its gravity magnifies that target further by pulling passing objects onto collision courses that a smaller planet could never create. In that sense, Jupiter acts less like a simple wall and more like a gravitational net. Objects that might otherwise continue on different paths are caught, altered, or removed from the inner system entirely. For Earth, this raises a profound possibility. Our planet's long history of relative survival may not be due only to luck or to the calmness of our own orbit. It may also depend partly on the architecture of the solar system beyond us, and especially on the presence of Jupiter. Without a giant planet in that outer position, the traffic pattern of comets and some asteroids could be very different. Over geological timescales, those differences might matter immensely. A world can be perfectly suitable for life in climate and chemistry, yet still face repeated sterilizing impacts if its neighborhood is not dynamically favorable. Habitability is never just local, it is orbital and historical as well. This is one reason Jupiter enters discussions related to the rare Earth hypothesis, the idea that complex life may depend on an unusual combination of conditions, rather than arising easily everywhere. Under that broad framework, a giant outer planet can matter because it helps shape impact rates, orbital stability, and the distribution of material in the system. Jupiter is not the whole explanation. Earth's habitability depends on many other factors, from its atmosphere and magnetic field to plate tectonics and the presence of liquid water. But if Jupiter has indeed reduced the frequency of certain catastrophic impacts over long stretches of time, then it belongs on the list of background conditions that made our history possible. The irony, of course, is that Jupiter's protective influence comes from the same qualities that make it dangerous. It protects because it dominates gravitationally. It shields because it destroys and redirects. It is helpful not because it is gentle, but because it is overwhelmingly forceful. The same planet that can tear a comet apart and alter interplanetary orbits may also have spared Earth from countless collisions we will never know enough to count. Jupiter's role, once again, is double-sided. It is a source of instability that may also be a source of long-term stability. It is a threat reconfigured into a form of protection. And this returns us to the larger emotional truth about Jupiter. Every time we think we have placed it neatly into a category, the planet refuses the reduction. It is the largest planet, yes, but also a gravitational architect. It is made mostly of the same elements as a star, but never crossed the threshold into fusion. It wears beautiful bands and storms, yet hides an interior where hydrogen behaves like metal. It generates a magnetic field so vast that it shapes the space around it. It presides over moons that include volcanic infernos, hidden ocean worlds, and ancient cratered archives. It intercepts impacts that are both catastrophic and illuminating. Jupiter is not one thing. It is a network of consequences. That is why it continues to matter so much to planetary science. Jupiter gives us a way to study atmospheric dynamics, extreme magnetic systems, giant planet interiors, moon formation, tidal heating, ocean worlds, impact physics, and the large-scale architecture of habitability, all at once. Few objects in the solar system connect so many scientific themes so naturally. To study Jupiter is not just to learn about a single planet, it is to study an organizing principle, a body whose existence changes the behavior of everything around it, and whose influence reaches from the sun's own subtle motion to the possible survival of life-bearing worlds. And for all we have learned, Jupiter remains unfinished. Juno has transformed our understanding, but it has not closed the case. The deep interior is still not fully resolved. The magnetic dynamo is still not fully understood. The atmosphere continues to produce surprises. The moons continue to raise new questions, especially Europa and Ganymede, as future exploration draws closer. Even the old image of Jupiter as a familiar bright planet in the night sky now feels incomplete, almost naive, compared with the layered system science has uncovered. The closer we get, the larger the mystery seems to become. Perhaps that is the most fitting ending for a world like this. Jupiter does not invite a clean final summary. It invites perspective. A giant beyond the asteroid belt, bright enough to catch the naked eye and powerful enough to move the sun around a shared centre of mass. A planet whose visible clouds are only a thin veil above a body of immense depth and pressure. A world surrounded by rings, storms, radiation, auroras and moons that may conceal oceans in darkness. A gravitational force that may have altered the fate of Earth itself. The more we learn about Jupiter, the less it feels like a distant object, and the more it feels like one of the central facts of our existence in this solar system. And somewhere out there tonight, while the inner planets continue their quiet revolutions, and Earth turns beneath its thin blue atmosphere, Jupiter is still doing what it has always done. Pulling, shaping, heating, shielding, disturbing, and waiting for us to understand just a little more of what that has meant all along.